brains form connections in 11-dimensional space. Welcome, beloved sibling. I am delighted to be here. I'm here with one of my favorite physicists in the world, Professor of Physics at Boston University, Nicholas Gross! And let us just say, a fellow improv science member.
Yes, excellent.
The reason we're talking right now is because there was a brand new study that came out that showed that brains form connections in 11-dimensional space. I understand that string theory and this 11-dimensional space business is a way of moving toward a single unified theory. The idea being that all the particles that we observe are merely strings vibrating in different dimensions. And that in order to account for all the different particles we observe being composed of a string, then those strings have to be vibrating in dimensions that we can't see.
That the universe has 11 dimensions comes out of string theory. Mathematics works in n dimensions, in any number of dimensions that you want. Mathematicians who study the field called topology.
Which is what these are the mathematicians who came up with this brain working in 11 dimensions. They are topologists.
It's a little bit different than the space dimensionality that the string theorists are talking about. So this is about how many connections a neuron has, the directionality of those connections. Neuron A passes information to neuron B, but it doesn't get it back. Based on this model of the brain that they've developed, is there are collections of maybe 10 to 12 neurons that are all connected to each other. So because it's got all those connections, that's referred to as a 10-dimensional or 11-dimensional. If it's got 11 neurons, they're all connected. So information gets immediately from any one neuron to any of the other. And that's what they're referring to as dimensionality.
I read it a couple of times, but I didn't understand because I'm not a physicist. Okay, that makes sense. Okay, so let me see if I can repeat what we're talking about here. Neurons are three-dimensional critters that make their connections in multiple directions.
Yeah, and maybe overlapping each other so they could be even higher dimensions. This is where you slip behind the cork, as it were. So the axons can sort of crawl over each other. And so I can have not only up, down, left, right, but then I can go in that other direction to connect up to my other buddy over there.
Nick, I got to tell you that it never occurred to me that this conversation would actually help me to make sense of this.
Okay.
Not that I didn't have faith in you, but it just seemed inscrutable. But this actually makes sense. I mean, so again, when they talk about multidimensionality, we're really talking about multidirectionality.
And connectedness.
Multi-connectedness over multiple directions. And multidimensionality is what the term of art that this particular bunch of mathematical topographists.
I think they're using it very, very technically. I think it's mathematically, it's a higher dimension. So now you can imagine if I wanted to plot out how all the neurons were connecting with each other and how their activity was going, I'd have to do that in my 11 dimensions of spreadsheets.
It always helps to talk to somebody who actually knows stuff. Thank you, my dear friend Nick Gross. I appreciate it very much. Your students at Boston University are blessed to have such a charming and knowledgeable professor.
Well, thank you, Aaron. I feel very warm and fuzzy whenever I talk to you.
Well, Nick Gross, Professor of Physics at Boston University. Thank you so much, my brother.
Bye.